Hello, we are going to review sorting algorithms. This is important because what I'm going to tell you here is Christoph's slides, but it's important that you know this before the exam. So let's review the big picture of sorting algorithms, because as the module passed during the months you were studying this, you were able to visit and study different sorting algorithms, but you never saw the big picture. And I think it's good for you to know the big picture about this. So the big picture is that sorting algorithms can be classified in two big categories. One is the comparison sorts. Most of the algorithms you have seen during the module are of this type. And the main characteristic of this is that they sort by making comparisons between pairs of elements. So usually these algorithms take a couple of elements and they decide which one is lower than the other one to decide in which position this element should be in the final array. The non-comparison sorts, as the name says, do not make any comparisons. So an example of a comparison sort is insertion sort. If you see the pseudocode here, you can see that here is the key comparison. So you are comparing element in position I with element in position J. And depending on what the result of the comparison is what instructions are made to rearrange the content of the array. We only saw one non-comparison sort, which was counting sort, and this is the pseudocode. And you can see here that in no part of the algorithm, the content of the element A is compared in terms of knowing whether it is higher than or lower than another element of the same array. We are just assigning things. In no part here you can see any comparison being performed. So this is the main difference between comparison and non-comparison sorting algorithms. Another comparison algorithm that is important to review is merge sort. If you see the pseudocode of merge sort, you do not see any comparison here, but that's because the comparison is made here. When you merge the two lists, which are already sorted, and you start to compare each element of the list to see how to merge these two so you get a sorted list. So the key part of merge sort is here, and counting sort again. So all the sorting algorithms you have seen so far are of the type of comparison sorts, except counting sort. So this is the first important thing you should know. The second thing that distinguishes comparison and non-comparison sorts is the data they work with. Comparison sorts work with general data. You don't need any special condition on the numbers you want to sort. Instead, non-comparison sorts need the data to have some particular characteristics, and that depends on the algorithm. In the case of the counting sort only works if you have integer numbers. Otherwise, you cannot apply counting sort. Other non-comparison sorts require other conditions, as numbers uniformly distributed in a range, etc. But for our course, counting sort requires integers. And without integers, counting sort cannot work. Please review the code and check why you need integer numbers. It has to do with the fact that when you fill the array C, you use the index of the array to identify the numbers. And also counting sort is efficient if the maximum number that in the set of numbers you have to array is small. Otherwise, it's inefficient, but not impossible to apply. Instead, comparison sorts do not need any condition on the data. You can use decimal numbers, integer numbers, letters, and transform them into their ASCII code. There's no problem at all. And finally, and this is very important, we have to check at the performance of these algorithms. In the case of comparison sorts, we have several worst-case scenarios, and insertion and selection and quicksort in the in the case you choose a really bad pivot they have worst case performance of n to the square, which is really bad. But merge sort and heap sort have a performance of n log n, which is much better. But counting sort is even better. It's the execution time is proportional to the size of the collection, which is fantastic. So the question is, can we get a comparison sort that performs as good as the counting sort? Because the problem or the limitation of counting sort is that I can only sort integer numbers. And here I can sort any number. So can I have the best of both worlds? This worst case complexity, but with general data? So what I'm going to explain you is not in any slide, but it's important for you to understand it. So please pay attention. So the thing is that if you are using a comparison sort, you can never get a worst case performance better than n log n. And that's a limitation of the comparison sorts. So I'm going to show you a brief demonstration of why this is so, and then I'm going to conclude this presentation. So let's say that we have a small array, just for the example to fit in this screen. We have a small array made of 3 elements, and we want to perform a comparison sort algorithm on this array to get the sorted numbers. So because I have 3 numbers, I can have 6 different possibilities of distributing the numbers in the array, but only one of them is going to be the sorted one. So the comparison sort has to pick the input and somehow recognize what of the 6 different possible ways of permuting these elements is the right one. Okay? In this case it's 6, but the permutation of n numbers in general is n factorial. So let's see in this small example, how is it that insertion sort identifies the right permutation. Okay? You can do this with any comparison sorting algorithm, but the explanation gets more difficult. Insertion sort is very easy to explain in this case. It's just the only reason why you usually see the example with insertion sort. So the first thing that insertion sort does is comparing the 2 first elements. We are going to build here something that is called a decision tree. It's a binary tree where you register the result of decisions. So the first question is comparing these 2, and you have 2 possibilities. Either the element in the position 0 is lower than or equal to the element in position 1, and in that case you know that in the final ordering, A0 should appear before that A1. Okay? And if not, it will be this other way. So after you ask this question, you have this. This is the next question you are going to ask. Since I already know that A0 is lower than A1, well, now I have to see whether A2 goes before A1, before A0, or after. So we are going to ask whether A2 is higher than or equal than A1. And in this other branch, we are going to ask exactly the same, but with A0, following the algorithm of insertion sort, when you take the third element and you see whether you have to put it immediately before this. So after asking this question, in this part of the array, we already know that A0 is lower than A1, but we need to know this. If A1 is lower than A2, then we have this situation. We know that A0 is lower than A1, and we know that A1 is lower than A2. So we don't need to ask anything else. We already know that the order is A0, A1, and A2. So we have identified one permutation. But if not, if A2 is not higher than A1, we have this information so far. We know that A0 comes before A1, and we know that A2 comes before A1, but we don't know how A2 and A0 are related to each other. So we need to ask about the order of this. So again, we can have yes or no. If it's yes, we know that A0 comes before A1, A2 comes before A1, and A0 comes before A2. So we know that this is A0, A2, A1. And in this case, we have found this other permutation. So we have already identified, the algorithm has already identified how to get to these three different permutations. If we follow the same reasoning to this part of the array, we will get the other ones. So we are going to speed up here. And this is the way you build the decision tree for insertion sort for three elements. So let's clean up this. I'm just eliminating the intermediate information for you to see the tree in a cleaner way. And what is interesting here is that this tree gives you all the possibilities. So for example, if we are going to sort 5, 8, and 2, we just navigate through the decision tree and we get to the right permutation for this input. Of course, different inputs lead you to different permutations. And the interesting thing here is that no matter what the algorithm here, at the end, the algorithm has to be capable to identify all the possible permutations. In this case, we have 6 permutations because we have 3 numbers and 3 factorial x is 6. But if we have n numbers, after we construct this tree, we are going to have n factorial leaves. And that's really interesting because the other thing we can realize is that we have 2 informations about this tree. One is that if we go back to here, you can see that the height of the tree is corresponds to the number of comparisons you have to make. So for example, in this case, we have to make 1, 2, 3 comparisons, and is equivalent to 1, 2, 3 jumps in the tree. So in the worst case, we have to make as many comparisons as the longest path in the tree. That's one important piece of information. The second important piece of information is that we know that this tree has n factorial leaves. And with these 2 pieces of information, we can know what is the worst case, because the worst case number of comparisons is the height of the tree. And we calculate the height of the tree because we know, here I have just put the same tree in just a smaller configuration. So we know we have n factorial leaves. We know that the height h of a tree, a binary tree of height a has a maximum of 2 to the h leaves. And we know that if we found out the value of h, we have the worst case number of comparisons because this is equivalent to the height of the tree. So we know that the number of leaves in a binary tree is never higher than 2 to the h. We know that in this particular binary tree representing a comparison sort, this number of leaves is n factorial. And now we need to find out what expression is for h. If we apply logarithm to this expression, we get that h is higher than log of n factorial divided by log 2. Because h is always higher than that, we can say that h is omega log n. And there's an approximation that says that n factorial can be approximated by n to the n. So log n factorial can be transformed in n log n. And that is the demonstration of why a comparison sort can never be better than that. So in summary, why we can never get a performance better than n log n when we are using a comparison sort? Well, there are n factorial possible permutations of a set of n numbers. Only one is sorted. If we build a decision tree of a comparison sort, the longest path, which is the height of the tree h, is the worst case for the number of comparisons. And it happens that the number of leaves of a binary tree is 2 to the h. And we know that for a comparison sort, the number of leaves is n factorial. So after we solve this equation, we get that h, what is the number of comparisons, is n log n. So this is the explanation of why a comparison sort can never get better than n log n complexity. So, in conclusion, if you need to sort in time proportional to the size of a collection, you cannot use a comparison sort algorithm because in the worst case, because it might be some cases where you can get linear, but in the worst case, you will never get linear with a comparison sort. So if you need to sort in time proportional to the size of the collection and the collection is made of integers in a limited range, go for counting sort, which is the only non-comparison sort you know in this module. See you in another video. Bye!